As many of you know, I'm a big fan of Mars exploration. And a couple days ago, a new research paper was published that explores a fascinating aspect of Mars history that I thought many in my audience would find interesting. So I want to take a closer look at this paper, and I'm going to talk about the most important findings of it. It's a paper from Geophysical Research Letters. I'm going to try to simplify it and put it into the context of why I think the results of this paper are important for the broader question of the age of Mars. So the question that confronting us today is, can ice layers tell us about the age of Mars? That's what we have coming up. Now, of course, my only interest isn't just in Mars exploration. If you're a follower of this channel, you know that I have an interest in young Earth creationism and the arguments that young Earth creationists make. And so young Earth creationism, as the phrase suggests, is the idea that the Earth is very young, only 6,000 years old at most. But sometimes people ask me, well, what about the rest of the universe? What about the rest of the solar system? And in fact, young Earth creationists are typically young solar system creationists, and they're young universe creationists as well, meaning that they think the entire universe is also very young. So that would imply, of course, that the Mars is also young, or approximately the same age of the Earth as the Earth. Now, there's two flavors for arguments for the appearance of the rest of the solar system. Either God created all the other planets and the rest of the universe to appear old. In other words, the appearances of age are just that. They're appearances of age, not actual age. Or God made them to appear young, or to appear as their age is, which is only 6,000 years. Now, it may surprise you that most young Earth creationists take the second approach. They say that God created the Earth as a young planet, and then all the features that we see on it today are the result of processes that have occurred since that creation. They apply this same logic to other planets. So if you take the surface of Mars, which has a number of different topological features, they won't necessarily go to the argument that God simply created it the way that it looks today, but will say that it has experienced a history of just 6,000 years. And yet they believe that possibly dramatic changes have occurred to Mars during just those 6,000 years, such that the volcanoes that are on the surface of Mars, the valleys that are on Mars, the ice caps that are on Mars, those, you have to admit, all have the appearance of processes that would have taken long periods of time. And so you might be tempted to say, well, since it would have taken too much time, maybe God just created those features as they are, therefore having the appearance of age. But no, many creationists will fall back and say, nope, that volcano is just, they try to explain it just like they explain volcanoes on Earth, as something that vast volcanic systems on Earth were simply a product of events that occurred during or soon after Noah's flood. They make the same excuses for Mars, which has volcanoes. They'll say that sometime in the last 6,000 years, there were dramatic events that occurred on Mars that constructed the topology of Mars as we see it today, even though we don't see much activity there now. All right, so we have this extreme contrast, right, of views. We have two worlds that are said to be only 6,000 years old, and contrasting that with the conventional approach or conventional way of understanding the history of both of these planets, which is that they're approximately 4.6 billion years old. We can see that contrast in just one quick example. Here we have the Institutes for Creation Research in an article, Our Young Solar System. And to them, as I just explained, they say the enormous amount of data collected by space probes in the last century strongly confirms that the planets, moons, and comets in our solar system are quite young. In other words, the observations that we make from our various probes that we have sent out in their minds, have sent data back that suggests those planets are young, rather than send data back that make the planets look or appear as if they're old, but nonetheless believe that they're young, therefore created with the appearance of age. So do they really look young though? All right. Do they really look young? And that's where we come to the paper that I want to discuss, because I think it sheds some light on this question. Do they, when you really delve down into the data and you start to analyze the surface of other planets, is it really obvious that the surface of these planets is young? Or is the simplest explanation for the observations we make that processes have been taking place over long periods of time to sculpt the surface features that we observe today? Let's get after that question. Before we dig into our paper, I got to introduce you to the most salient feature that's going to be at the heart of what we're going to talk about. So here are two images of the planet Mars. They have a North Pole and a South Pole, and on those poles they build up this dry ice, that's carbon dioxide, frozen carbon dioxide, and water ice. And so you see these white caps on both of the poles. And those white caps will wax and wane during the seasons, because Mars has seasons just like Earth does as the planet rotates around the sun. So if you take a close-up image of one of those poles, you get something like this. This is just a few miles across. So you're taking a very small section here, and there's sort of this layering. All right, so this potentially represents layers of ice that have built up over many, many different years. So more ice at times in the history of Mars, more ice has built up than has sublimed in any particular summer season. And then more ice builds up again in the winter season for whichever pole we're talking about. And then some of it evaporates again, and then more builds up. And you end up with these very amazing layered structures that are seen from satellites. All right, with that background, we're ready to get just a little bit more geeky with this. All right, we got to get a few details out of the way, preparatory work, in order for us to understand the significance of the results of this paper. So warning, super geeky, astrophysics, geology, and comparative planetary climatology is what's coming up. So before we can talk about Mars, we have to spend just a few minutes talking about the Earth first. And specifically, we're going to talk about the rotation of the Earth around its axis and around the sun. So the patterns that are seen in history due to changes in these patterns are called Milankovitch cycles, named after Milankovitch. And the two we're most interested here, because they're going to relate to our paper we're going to look at in a moment, about Mars, are precession and obliquity, or tilt, right? I think everybody understands that the Earth is tilted with respect to the sun, because that's where you get your seasons, right? When the northern hemisphere is tilted toward the sun, it's our summer. And then as the Earth goes around the sun, eventually it reaches a point where the northern hemisphere is faced away from the sun, or tilted away from the sun, so isn't receiving as much direct sunlight, and so is cooler, so therefore our winter, and the southern hemisphere is closer to the sun, therefore their summer. All right, so there's that tilt. What many people may not understand, though, is that tilt is changing. All right, and that's an observation. We could say that's a fact, right? We can measure the fact that the tilt of the Earth is very slowly changing. Right now, it is tilting so that it's tilting back straighter up. All right, so currently it's at 23.5. Actually, I read it's 23.44% now. And so that tilt is getting to be smaller and smaller and smaller relative to the sun. And if you were to measure that tilt over time, or extrapolate back, you'd see that Milankovitch and others have calculated that every 41,000 years, it's going to go through a cycle of tilting from 21.5 to 24.5 degrees. All right, that's obliquity. Then you have precession. The precession's a little harder to visualize, but there's a little top right here in this picture. And that's a pretty good way of thinking about it, right? As a top spins, it begins to also spin, well, not spin, but it begins to process, all right? All right, so it forms its own rotation. And so that's what the Earth is doing too, right? The Earth is spinning on an axis, but then that axis is actually rotating, all right? And that's precession. And so it's tilted, and the tilt is changing slightly over time, but it's also processing, all right? So it's rotating. So the Earth is not, I guess you could say the Earth is not stable, right? It is gradually changing its tilt, its precession, and its eccentricity, all right? So the shape, right, of its trip around the sun changes slightly over time. All of these are measured, right? Things that we can actually measure and see are happening today over the past, 50 years. We've got excellent measurements. And then what you can do is you can extrapolate back and you say like, well, how long would a one precession take? Right? A precession would take 19 to 24,000 years to complete. And obliquity, 41,000 years in order to affect this particular tilt back and forth as we're flying through space. All right, and eccentricity takes an even longer period of time. Well, you can see there's an obvious conflict here with the young Earth creation model. All right, they're not going to accept that the Earth has gone through an entire precession, or that its tilt is going back and forth well, they might think that it went back and forth, but they must have thought it went back and forth at a much faster rate in the past if they think it happened, because if it takes 41,000 years, that's enough time to go through 7 different cycles. And so they naturally object to any evidence of Milankovitch cycles in the Earth's history. But if you look at the ice cores from Greenland, and there's a number of other different sources of data in sediments that you can look for these changes in patterns. Now, why would you have changes in patterns? Well, as the tilt changes, you're going to change summer and winter patterns, right? So there are going to be times where the Earth is colder. There's going to be times when the Earth is warmer, and that's going to change the climate. And that should be reflected in like ice buildup at different times in different years, and sediment buildup and other things, right? And so you can map onto ice layers and see that there are roughly these rhythmic cycles in the ice layers that seem to match some of the predicted Milankovitch cycles. All right, so that's really interesting and fascinating evidence that actually the Earth is very old, that it's actually gone through not just one cycle, right, of one precession cycle or one tilt cycle, but it's actually gone through many, 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 many of them. In this case, this is obliquity, so the tilt. And if each one takes 41,000 years, then you're looking at hundreds of thousands of years, in an ice column to be able to explain this particular pattern. Okay, now the question's going to be, can we find similar evidence on Mars? Right? Can we see on Mars that maybe Mars is also going through these similar cycles? And the paper is from Geophysical Research Letters. Sori et al. Just published a few days ago. And title, Orbital Forcing of Martian Climate Revealed in a South Polar Outlier Ice Deposit. That ice deposit is in a very large crater that's some 10 to 20 kilometers wide. And inside this crater, there's a massive water ice deposit. Now, fortunately, they include a plain language summary, right? A lot of papers today, they'll have their abstract, which may still have a lot of jargon in it. So they publish also, along with their abstract, the plain language or simple summary. Understanding the relationship between Martian climate and changes in the planet's axial tilt and orbit around the sun, is one of the most important goals in Mars science. Most past studies conducted to address the goal have involved the study of polar ice caps, huge sheets of water ice at the North and South Pole. Here, we instead study smaller ice deposits, tens of kilometers in diameter, near the North and South Pole, but located within craters and separated from the large polar caps. So they're going to represent one location's record of climate history. We find that the ice deposit in Burroughs Crater contains particularly good evidence that recent Mars climate is strongly controlled by changes in the planet's orbit and axial tilt. So what they're claiming here is that they have evidence by looking at the ice in this crater that Mars has undergone multiple different climate changes, and those climate changes follow a pattern that fits the pattern of their planet's orbital and axial tilt. Right? We've looked at Mars. We've measured Mars. We know the speed it's rotating. We can follow its pattern around the sun, and we can measure its tilt, right? Its obliquity compared to the sun. And we've estimated the amount of time it's going to take for the precession of Mars, for the tilt, how fast the tilt is changing, and looked at the changes in the rotation of the orbit around the sun. And that's just pretty much just math, all right? It's making observations and then back calculating in time to see where something was in the past and what its tilt was. And then from that, climatologists will look at that and say, oh, well, if Mars had a tilt of this at this particular time, 10,000 years or 100,000 years ago, we would expect that the climate would have been colder. And then at this particular time later, it would have been warmer, X number of years later. All right? All of that is something that can be predicted. All right, so you come in with this prediction just based on your observations of the tilts and the axis currently and your measurements of how they're actually changing in the present. Extrapolate into the past. So now you go to a crater, and in this crater, you have a huge amount of ice, which we're going to see is like more than 500 feet thick of ice. And you observe that this ice has very distinct layers. All right, so there's a whole bunch of layers to this ice. So you can think it's like the ice caps in Greenland. There are distinct layering in those ice caps. So they went ahead and they measured across this ice, and what you're seeing in the color here is the elevation. So we have lower elevation and higher elevation. And as we go from 100 meter, like 120 meters, all the way down to some 300 meters, so almost 200 meters of ice, they're looking at the edge of this ice. And the interesting thing about this ice is what makes the layered appearance, which isn't as obvious here as it is here. All right, you'll see these different colors. Those different colors are not only just different densities, like there's more dust in those layers versus clear ice in the layers that look whiter. There's also an elevation difference, or what they're calling protrusion. And you can think of protrusion as the way this ice is. It's kind of like there's a flat layer and then it falls off, and there's another little flat layer and then it decays off, and there's a flat layer, decays off, and so forth. And so what they're seeing is that there are little tiny protrusions in this ice. It's not just a flat surface. And each of the protrusions, where these flatter areas are, that represents areas that are not subliming as quickly, because that's what's happening to the ice at the edges of this massive mound. And they're darker. So they seem to have a lot more dust in them. So during those particular times when the ice was laid down, there must have been a lot more dust in the atmosphere that collected in that. And all that extra dust has somehow resulted in a reduction in the amount of evaporation. You might think it would be opposite, because usually we think of darker dust as leading to heating up, but it's so cold there anyway. There's a different relationship. So anyway, you have these darker layers and you have lighter layers, and those result in different amounts of water loss, leading to this bumpiness. And so they can measure that. And so what they get is, this is the protrusion amount, right? It's actually a fairly large numbers in some cases, many, many meters. And so you get, well, and just look at this. You can see there's a pattern here, right? It's like, it's pretty obvious there's some kind of pattern. There's blips here. And so are these, you might ask yourself, are these annual layers? Like every single year, a certain amount of ice is deposited. So maybe one is the summer months and then you have the winter. And so that's the difference. This is in the Greenland ice cores. You count varv, basically like varv, they're annual layers of ice. No, that's not what is thought to be going on here. It's thought that this ice has built up over long periods of time, but during some of those periods of time, the climate was experiencing dramatic changes. And those dramatic changes could have been a result of the obliquity and the approximate location of Mars compared to the sun. And so let's get right down to the final result here. They found that there was a 2.4 ratio of dominant wavelengths in the 188 meter stratigraphy. All right, so this nearly 500 foot thick layer of ice, there's a 2.4 ratio of dominant wavelengths. All right, now the whole wavelength thing is this. All right, there's a prediction made based on looking at the Mars obliquity changes. They predict, in other words, physicists using math, all right, and measurements say that the obliquity should be changing on a cycle of 120,000 years. Should go through a cycle of axial tilt every 120,000 years based on what it's doing today. And the precession of Mars, remember the precession is this wobble. That's the word I was looking for before. It's wobbling, the axis is wobbling, and it wobbles approximately 51,000 years. So it takes 51,000 years to do that wobble. Right. For Earth, it's only 19 to 24,000 years. Now, those are two different ones. Now, once in a while, you're going to get the wobble and you're going to get the axis tilt lining up in such a way you're going to create the most extreme climate situation on Mars. And then at other periods, they're not lined up, and so you're going to get a whole mixture of different effects. All right? The cycle should be 120,000 and 51,000, but both of those things, to each one individually, probably doesn't create enormous differences in climate. But when the two line up together, either pointed toward the sun or being farthest away from the sun, you're going to expect your most dramatic changes. And what you predict is there's a 2.4 ratio, right? There should be you should see a ratio between these blips of every 2.4 of one thing, you see the other. And this is what they get. Otherwise, you predict that you should see certain patterns in the ice layers if they're being laid down over long periods of time. And you should see the most dramatic effects on climate at this ratio. And this is what they observe. Right? So that's been proposed to control recent ice accumulation. This match between ratios is what has previously been argued to be the requirement for confident detection of an orbital signal in Martian ice. Right? So prior, somebody had already predicted that we should be able to look in the ice, and if the ice has been building up over long periods of time, it should be going through cycles that are much like Milankovitch cycles on Earth. But they should be based on the ratios of those cycles on measurements of the Mars precession and the Mars obliquity changes. And since we can measure those and we know what we should find, it's a prediction. Then they go and they find a particular crater that has a very thick layer of ice. And from satellite, they can see the edge of this ice and they can see this pattern that they can then count the rings essentially and figure out the distance, the amount of space between each one of the darker rings. And they get a confirmation of their prediction, right? That you should be able to see this particular pattern, and that's what they see in this particular ice. Now, once they establish that this appears to be really time intervals of 120,000 years, right? And they have this wavelength of, well, I don't want to go into the wavelengths. That has to do with there's these big dips and then there's minor ones in between because they represent the 151,000 years and so forth. All right. All of that is to say, they found that the difference between these different time frames, in other words, the difference between these different peaks should represent about 51,000 years. And since they have the measurement of the amount of material that was deposited during that 51,000 years, right? Between here and here and here and here and here and here and so forth, they can figure out an average amount of material that's been deposited. And what they find that is they discover that the average accumulation rate, now remember this is an average, and they see that it's not always the same because the distance between these is somewhat, the periodicity is the same, but the total amount of material laid down might change slightly. So the average 0.13 millimeters per year. So it's a very, very small amount, right? But over 51,000 years. All right, so it's probably years in which there was happened to be a lot of material laid down, and then it sublimes, a lot of it disappears. And the next year, some more is added, some disappears, more is added, more disappears. But during thousands of years, you essentially get the same kind of ice. And then you move through a phase in which the Mars is moving into its obliquity has changed gradually, and its precession has changed to the point where, now it's a lot colder. Now we're laying down more ice during those years, and maybe it's drier at that time, and also there's a lot more dust in the atmosphere. So during those years, which may be thousands of years, right, you end up laying down a layer that's a foot or a couple feet thick that has a tremendous amount of dust also incorporated into that water. And then the obliquity changes, is changing gradually. You go back to a previous climate, and then you start laying down additional ice layers on top of that. So overall, what they're suggesting is that because this pattern fits the pattern of their expectations, it means that there are Milankovitch cycles embedded in the ice layers of Mars. And we know from our observations and our measurements that those Milankovitch cycles should only occur every 120,000 years and 51,000 years for these two different measurements. And there's been multiples of those cycles, right? So overall, they suggest that 188 meters was put into place over a period of 1.4 million years. Now, that's nothing like the overall age of Mars. All right, but this is inside of one crater. And it suggests to them, too, that the climate of Mars has been relatively consistent, other than these cycles, all right, for the last 1.4 million years. And that kind of fits with other observations in other parts of Mars, that Mars has not had dramatic changes in its overall appearance over the last few million years. Now, none of this can be true for the young Earth creationist. Right? They have to look at these layers, and they have to see this pattern or this periodicity pattern in these layers, and they have to just tell themselves that's something that must have happened in just the last 1,000 years, and that the pattern doesn't really mean anything. The fact that the pattern is the same pattern as predictions from the rotation, the axis of the actual planet itself, must just be a sheer accident. But the fact that Earth has patterns that fit the patterns of our stellar object, the Earth, and its rotation. And then Mars has a different rotation, a different axis, a different change in terms of its precession. And then you find a matching pattern on Mars that fits that, right? Both of those, it's one thing to say that one is just a coincidence, but then you'd have to have a coincidence on Earth and you have to have a coincidence on Mars as well. The simplest explanation for this data is Mars is really old, right? At least in this case, 1 million years old. It's taken 1 million years to emplace that ice into that particular crater. Then you have to consider the crater itself, right? The crater has walls that have eroded, and the crater itself must have been produced by it seems apparent that it was created by being hit by an asteroid, right? And that's dug into, and now that we've been to Mars and we've looked into craters, you can see there's actually sediments on the crater walls. So that means sediments had to be laid down before that, before you made the crater. Then you had to fill it with the ice, right? When you start stacking all those things on top of one another, all of those are a series of historical events. And each one of those events could have taken a long time. Well, other than getting smacked by an asteroid. That's like in an instant. And young Earth creationists will look at those same craters and say, God wouldn't have made a creator, because that's not all creationists say this, but many do. They'll say like, that crater is a blemish, right? That shows that there's like things happening that are out of control in the solar system. So what they'd say is that happened sometime after creation. God didn't create Mars with a bunch of blemishes all over it of these being whacked with space rocks. And also they look at those layers and they say, well, where did the layers of sediments come from? Oh, they must have come from, well, maybe a global flood would happen on Mars at the same time it happened on Earth. And if you laugh at that, go to the Ark Encounter and they have a display on the wall there that talks about the flood on Mars happening at probably the same time on Earth, because whatever cataclysmic event happened to Earth to maybe start the cataclysmic flood here may have also affected the other planets, which means that crater is only 4,500 years old, which means the ice inside of it must be younger than that. So all those layers of ice, all 500 feet of ice, has to be something deposited over a very short period of time. But why does it have a pattern? All right. Why does it show a particular pattern that appears to match the pattern of tilt changes in the planet itself? Because I don't think young creationists can say that the Mars was basically quivering there and changing every 25 days. It was tilting back and forth at the same time ice was being laid down. Because you'd also require, in order for the ice to be different, you'd have to change the climate every 25 days in order to get this distinct layering of ice. You see, I could just go on and on and on here, and just add on one more problem after another. The simplest explanation is that Mars is old and that it has been processing, that it has been tilting gradually, that it has changed its orbit gradually over time. That has affected the climate on Mars, which has changed the deposition of both sediments and of ice layers on Mars over time in recognizable, predictable patterns. That's the simplest explanation. So when I see young Earth creationists say that we've sent probes out there and all the evidence suggests that the solar system is young, this doesn't suggest the solar system is young. There's nothing about this data that looks young. It looks old, right? That's the simplest explanation for the data that we observe. All right, that's my story of Mars age, and Milankovitch cycles as appearing on Mars. My name is Joel Duff. You can find my writing on thenaturalhistorian.com. And please subscribe to my YouTube channel and hit like maybe if this video was likable. We'll talk to you later. Bye-bye.